In this video, we solve a system of differential equations subject to initial conditions using the Laplace transformation. We'll start in the same way that we always start. We introduce our notation. Let's let the Laplace transform of x of t be capital X of s, and the Laplace transform of y of t be capital Y of s. And then we'll take the Laplace transform of both sides of each of these differential equations. I'll use this notation to indicate the Laplace transform of each side of that differential equation, or to indicate that idea that we're taking the Laplace transform of each side of the equation. So we'll introduce the notation. That way, anybody who reads our work knows exactly what we mean by x of s and y of s. And then we'll take the Laplace transform of the first differential equation. And of course, dx dt is the same as x prime. And the Laplace transformation is a linear operator. So you can apply the Laplace transform to each of those terms. So this is the first derivative. The Laplace transform of the first derivative has two terms. One is s times x of s, and then the other one is minus little x at 0. And we'll just do the same thing, just evaluate those Laplace transforms on the other side. And then we'll use our initial condition. We're told that x of 0 is equal to 2. So that is the Laplace transform of the left-hand side of the equation set equal to the Laplace transform of the right-hand side of the equation. Now we want to rewrite this so that all the x's and y terms, x terms and y terms are on one side, and all of the terms that do not involve x or y are on the other side, because we're going to solve the system of equations using Cramer's rule. So I would subtract 3 times x of s from both sides, and then factor out that x of s, and then subtract y from both sides. And then add the 2 to both sides, and you'll end up right here. So that is our first equation involving our two unknowns, x of s and y of s. Now we want to find the second equation by doing this. Same thing. Take the Laplace transform of the second equation. dy dt is the same as y prime. Then use the linearity of the Laplace transformation to compute the Laplace transform of the right-hand side. And so we end up with s times y of s minus little y at 0 equals all of this. And then we want to use our initial condition. So y of 0 is -1. Then if I rearrange this equation, I could add the x of s to both sides to get all the x's on this side and subtract 3 times y of s from both sides and factor out the y of s. And this is a plus 1 on the left-hand side, so I'd like to subtract it from both sides. We end up here. So we've got 2 equations and 2 unknowns, and that can be solved any number of ways. I don't know if it's any number of ways. It can be solved in many ways, several ways. You could solve by elimination. You could solve using the addition method. Multiply this equation by s minus 3 and then add them together to get rid of the y's. Multiply this equation by negative quantity s minus 3 and add those together to get rid of the x's. Or you could use Cramer's rule, and that's what I'm going to use here. And the system of 2 equations and 2 unknowns can be written in matrix form this way. we have s minus 3 times x of s minus 1 times y of s is equal to 2 minus 4s. So that first equation can be written this way. It's a dot product of this first row of this matrix and the column, this first column here. The dot product of the first row and first column gives us the first row, first column entry over here. For the second equation, we can use this second row and this first column. The dot product of the second row and the first column gives you the second row, first column entry here. So we have 1 times x of s plus s minus 3 times y of s equals -1 minus 2 over s. And then we can solve this using Cramer's rule. Now, according to Cramer's rule, provided that the determinant of this matrix, oops, that should not be a plus sign there, provided that the determinant of this matrix is non-zero, so that means that this system of equations has one solution, then the x value for that solution is given by this. It's a quotient of two determinants. The determinant of the coefficient matrix goes in the denominator. And we want a similar determinant in the numerator, but we swap out that first column with the column on the right-hand side. So we've got 2 minus 4 over s and -1 minus 2 over s. And the second column stays exactly the same. So we'll have this times this. If we distribute, we'll have first times first is 2s. Outer times outer is -6. Inner times inner is -4. And last times last is plus 12 over s. And then we're subtracting this times this. So that means we're subtracting a quantity of 1 plus 2 over s. When we subtract, we'll distribute the negative. We'll end up right there. In the denominator, we have s minus 3 times s minus 3. And then we're subtracting a -1, so that means we're adding 1. And then if we simplify this, we end up with 2s. And then I have -6 minus 4 minus 1, that's -11. And then 12 over s minus 2 over s is 10 over s. Okay, so that's x of s. And I don't like to have those complex fractions, so I will multiply the numerator and denominator of this by that denominator to clear the fractions. So it's multiplied by s over s. So we have x of s equals 2s squared minus 11s plus 10, all divided by s times the quantity s minus 3 squared plus 1. Now we could just do partial fractions from here, but I think I want to simplify further. No, actually it's not going to be worth it. Let's just do partial fractions from here. I've got an irreducible quadratic factor here, because if I tried to set this equal to 0 and solve for s, I'd get complex numbers. I'd get s equals 3 plus or minus I. And then I have a linear factor that's not repeated, it's just an s. So the partial fraction decomposition for this is a over s plus, for an irreducible quadratic, we've got a linear expression in the numerator over that denominator. Now this irreducible quadratic expression, if we distribute, we'd have s squared minus 6s plus 9 plus 1, which is plus 10. In order to find a and b and c, we'll take this equation and we'll multiply by the LCD, which is the original denominator. When we do that, we'll have this numerator equals a times, Well, what we would get if we took this fraction and we multiplied by this. Well, in that case, the s's would reduce and we'd be left with this irreducible quadratic. So that's an s squared minus 6s plus 10. And then over here, when we multiply this quotient by this will cancel with this, and the only thing that will be left is the bs plus c and the extra factor of s. Oops. Now, in order to solve for a and b and c, I will just choose a couple of values for s, 3 values for s, that will allow me to solve this system of equations, or allow me to solve this equation for a, b, and c. Not a system, it's just a single equation. If s is equal to 0, we get 10 over here on the left-hand side. It's 2 times 0 squared minus 11 times 0 plus 10 is just 10. And then we'll have a times 0 squared minus 6 times 0 plus 10. So it's going to be a times 10 as well. And then we have bs plus c times s, where s is 0, so that's going to be gone. So we have 10a equals 10, so that means a equals 1. Then if s is equal to 1, well, you can pick any s value you want now. Since I can't make this equal to 0, I'll just pick any s value I want. The next choice, the next easiest choice after s equals 0 is s equals 1. So if s is equal to 1, we'd have 2 plus 10, which is 12. 12 minus 11 is 1. And if s is 1, we'll have 1 minus 6, which is negative 5. Negative 5 plus 10 is positive 5. And then I have b plus c times 1. And since a is 1, this is 1 equals 5 plus b plus c. So that means that b plus c must be equal to 1 minus 5, or negative 4. Great. We still don't know what b or c are, but we are very close to figuring out what b and c would have to be. So I would choose another value of s. You can pick any value of s you want. I'll choose s equals negative 1. If s is negative 1, we'll have 2 minus 11 times negative 1 plus 10. So that's 2 plus 11, that's 13. 13 plus 10 is 23. And that's equal to a times what we get when s is negative 1. We're going to have 1 plus 6 plus 10. And a is equal to 1, so it's going to be 17 plus bs plus c. So it's going to be a negative b plus c times s, which is negative 1. So if I distribute that negative, I have b minus c. Plus 17 is equal to 23. So if we subtract 17 from both sides, we get b minus c equals 6. So we know b plus c equals negative 4 and b minus c equals 6. If we add those together, we eliminate the c's and we get 2b equals 2. So b must be equal to 1. And if b is equal to 1, we have from here 1 plus c equals negative 4. So c must be negative 4 minus 1, or negative 5. So x of s can be written this way. It was a over s, where a was 1, plus bs, so that's 1s, plus c, which is negative 5, over this expression, which is the same as s minus 3 quantity squared plus 1. Now, in order to compute the inverse transform of this, I need the numerator and denominator to match here. This looks like an s squared plus k squared, where the s has been replaced by s minus 3. So that's going to remind me, or that reminds me of my sine and cosine Laplace transforms. But if I have an s over s squared plus k squared, that would give me a cosine, or if I have a constant k over s squared plus k squared, that would give me a sign. But if the s has been replaced by s minus 3, I need an s minus 3 in the numerator here. So in order to make it look like that, I will write this s minus 5 differently. I'll write that as s minus 3. That's what I want it to be, plus negative 2, because s minus 3 minus 2 is s minus 5. And if I'm using my inverse transforms, this is f of s minus 3. And this is f of s minus 3 as well. And remember our rule for f of s minus a. The inverse transform of f of s minus a is e to the at times the inverse transform of f of s, which is just f of t. So that's what we're going to apply here and here to compute our x of t. And we can take the inverse transformation, our inverse transform of each of these pieces, just term by term. The inverse transform of 1 over s is just 1. The inverse transform of this, well, if this is f of s minus 3, that means our a is equal to 3. So we'll have an e to the 3t times the inverse transform of exactly the same expression where the s minus 3's have been replaced with s's. And this is also similar. We've got an f of s minus 3, and I'll factor out the negative 2 as well. So I'll have negative 2 times e to the at, where a is equal to 3, so that's e to the 3t, times the inverse transform of 1 over s squared plus 1. Since k squared is 1, that means that k equals 1. That's true for both of these. So the inverse transform of that piece is going to be cosine of t, and the inverse transform of this piece is sine of t. Okay, so that's our x of t. Now we could use the Laplace transformation to find y of t as well. We could use Cramer's rule again. Let's use Cramer's rule again to find y of s. So that denominator looks like this. That's our coefficient matrix. So that hasn't changed. But when we're finding y of s using Cramer's rule, we leave the first column alone and we replace the second column with the right-hand side of our system of equations. So we'll have 2 minus 4 over s here and negative 1 minus 2 over s there. When we distribute, we get negative s. It's first times first, outer times outer is negative 2, inner times inner is positive 3, and last times last is 6 over s. And then that's on this diagonal, and then we're going to multiply across that diagonal and subtract. So we're subtracting this quantity, so we'll subtract a 2 and then add a 4 over s. Well, that's going to lead to a negative s. Then we'll have a minus 4 plus 3 is minus 1. And then 6 over s plus 4 over s is 10 over s. And all of that is over s minus 3 squared plus 1. And to get rid of the complex fraction, we'll multiply numerator and denominator by s over s. If you want, you could factor out the factor out the negative 1 as well, but I don't think that actually helps us in this case. And if I'll distribute here because I'm about to use partial fraction decomposition. Okay, so that's my y of s. And in order to get it into a form so that we can take the inverse transform, we'll use partial fractions. So this is a over s plus bs plus c over s squared minus 6s plus 10. And if we multiply the numerator and denominator by the LCD, which was just the original denominator, these reduce and these reduce, these reduce and these reduce. And so we get this. Very similar to what we got when we were solving for solving partial fraction decomposition problems for the coefficients in the decomposition for x of s. So I would let s equal 0. When s is equal to 0, we get 10 on this side equals 10a. So we'll have a equals 1 here. And then I would choose s equals 1 next. This will be 10 minus 1 minus 1, so it's going to be 8. And if s is equal to 1, we're going to have 1 minus 6 is negative 5. Negative 5 plus 10 is 5. And we'll have b plus c here. Since a is 1, this is 8 equals 5 plus b plus c. So b plus c is equal to 8 minus 5, which is 3. Then I would let s equal negative 1 next. Well, then that would be negative 1 plus 1 plus 10 equals, if s is negative 1, we'll have 1 plus 6 plus 10, so that's going to be 17a plus negative b plus c times negative 1. So we'll have 10 equals 17 plus b minus c. So from that line, we have b minus c equals negative 7. So I've got 2 equations and 2 unknowns. We could add those together to get b. So we had b plus c equals 3 and b minus c equals negative 7. If we add those together, we get 2b equals negative 4. So b must be equal to negative 2. And then if b is equal to negative 2, then we'll have negative 2 plus c equals 3. So c must be equal to 5. So y of s is equal to a over s, that's 1 over s, plus b s plus c over s minus 3 squared plus 1. Now here's a case where I would use a well-chosen 0. I need to have an s minus 3 in the numerator in order to use that inverse transform that involves the exponential and the cosine function. So I would take that negative 2 as a factor, and I would take it out. And instead of writing a negative 2s, I'll write negative 2 times s minus 3. I'm just going to make it what I want it to be. That 5 is still there. And then to compensate for subtracting that 3, I will add a 3. And then I'll group these 2 together and distribute that negative 2 to both of the terms, and then simplify. So we'll have 1 over s, and then we'll have a negative 2 times that, s minus 3 over s minus 3 squared plus 1. Negative 2 times positive 3 is negative 6. Negative 6 plus 5 is negative 1. Okay, actually all of these are ready for computing an inverse transform. So the inverse transform of 1 over s is just 1. And then we're going to have 2 here. Since s has been replaced by s minus 3, we'll have an e to the 3t there. And then the inverse transform of s over s squared plus 1 is cosine of t. Since s has been replaced by s minus 3, we'll have an e to the 3t there. And then we'll multiply by the inverse transform of 1 over s squared plus 1, which is sine of t. So that is our y of t. So now we've got y of t, and we have x of t, which we found earlier. So the solution of the system of differential equations is an ordered pair. It's x equals this, and y equals this function right here. And we were able to solve using Cramer's rule. You could solve differently if you wanted to, but I chose not to this time. And this is the original system of equations. If we take the derivative of x, it turns out to be 3 times the original function x plus y minus 4. And if you evaluate x at t equals 0, you get 2. And if you take the derivative of y, it turns out to be the same as this function on the right-hand side here. And if you evaluate this at y equals 0, you're going to get negative 1. Or excuse me, at t equals 0, you're going to get negative 1. So that's the solution of our system of equations using Cramer's rule and the Laplace transformation method.